history. An investigation occurs in this room, and they're trying to investigate, what Brian Carrier did. They're going to analyze the objects to find out, when there was contact between, Brian Carrier and this object to find out, if I'm in the history of these objects. And the basic concept is that the history is never fully known. But the goal of the investigation is to determine that history as much as possible and try and make inferences about that history. So this is kind of clear and kind of, we can see this for the physical world where, witnesses are used to see what they saw about an incident, or, objects are analyzed to find out who touched them or what they've been in contact with. So the question is, what is the history of a computer? Because they don't really have senses as we do. So the basic argument in this work is that the history of a computer is basically the sequence of states and events that have occurred in this system. And this is kind of, again, a theoretical notion, and this doesn't always record it each time, but it's this notion that the sequence of events that occur in the computer are its history, and it's what we want to determine with the investigation. And as we'll see later, these occur at both primitive and abstract levels. Primitive meaning CPU registers, CPU instructions, hard disk sectors, the core low-level events and states that occur in a system. And there's abstract events and states as well, like files, system calls, or user-level events of clicking on buttons and various things that occur at multiple levels. And basically, digital investigation is basically a process where we make inferences about the previous states and about the previous events that occurred on the system, maybe given only one state of the system. We try and figure out this other history of it. So now we kind of get into some of the formalities of this. So the basic concept of this whole model is based on a finite state machine definition. And so for those of you who have forgotten or want to forget about all these various things, the three parts we're concerned about for the finite state machine definition is we have a set of states, which we're defining as Q. And this set basically contains all the possible states the system can undertake. And basically, if any bit in the system changes, we're in a new state of the system. We have a set of possible events, which are in our alphabet. And these basically denote which events are possible in the system, which are supported by the system. And there's a state change function which maps a given state and a given function in a given event to the resulting state from that event. Now, the important thing here to note before everyone says, this is bull, that we're not saying we're going to represent the computer by a finite state machine during investigation, because that's quite clearly impossible, or not impossible, but pretty much impossible to do with a modern computer that has millions of instructions and gigabytes of RAM and gigabytes of terabytes of storage. It's just not possible to actually represent that as a useful finite state machine. But we're using this as a general theoretical model so that we're not limited to any certain architecture or system. So as I said before, there's histories at the primitive and the abstract level. The first thing we're going to address is the primitive state history. And it's basically, with this, we're going to address again. Now it's going to jump ahead like 5 slides at me. Yep, see? All right, so the history itself maps a time to a state in our set Q, which is our finite state machine definition. So we have this counter, this notion of time. We won't get into the details of this right now, but there's this notion of a time that basically the history maps a time to whatever state existed at that time. So I get in trouble now. All right, forget all these animation things. So we have this set of one of the problems with this, though, is that in a real computer, this set Q, which contains the possible states the computer can have, can be different at 2 different times. Anyone know why? So if you add a USB token or a floppy disk or a CD-ROM or any other storage device in the system, we now have an entirely new set of possible states in the system. So if we want to account for the history model to account for the entire history and possible states of the system, we actually need to account for which various storage devices were connected at each time in the system. So our finite state machine model actually has to account for this, that the set Q, which has our possible states, is a dynamic set that's going to change, or could possibly change for each time in our history. So basically the model needs to map each time. The model needs to map each time basically to the set of devices that were connected that time. And we also need to know what possible states for each device. So we actually need to basically combine all these various things of knowing the possible states for the device, which devices were connected, before we can define what our possible states of the actual system are. And we basically determine the possible states by how many addresses there are on the hard disk or other storage device, what the domain of each address is, what are its possible values, and we merge these and combine these and work our way up to define our set Q, which we can then map to for the state at that given time. And examples of this state include registers in the CPU, hard disk sectors, memory bytes, all the low-level things that we never really care about, but are the underlying storage devices of the system. So that's the primitive state history. We also need a primitive event history. All right, I'm just going to go ahead here until we get them all. All right, I don't know why I understand this, but so basically our primitive event history is mapping a time itself, again, this time value, to an event in our alphabet that occurred during that time frame. And again, in the same case, the set of possible events that can occur at two times are different because we can have two different sets of event devices that are connected. So our model needs to map each time to the set of devices that were connected, and we also need to know which events were possible with each device. So, for example, low-level primitive events are CPUs, memory management units, other low-level processors on the system that can change the actual state of the system at any time. So here's a basic example of what we're referring to here. That this column here is basically we're representing as a storage device or a set of storage locations. So these are registers, R1 through R7, for example. So at time t, the value of all of these represents the history of the state at that time. We have some event here that occurs at time t that maps, that writes a new value to this register R3. And so the state at time t plus delta t is now whatever values are in all these registers at this time. So this is the second history marking. And this goes on and on and on. This entire process, we have events followed by new states, followed by new states and events. So basically, in summary, for the primitive level, hold on a second. We define the capabilities of each storage device and event device as our first basic thing. Then we define which devices were connected each time. And then we determine actually which actual state or event occurred. But there's a problem with this underlying process is that who really cares about primitive states and events? When was the last time you heard investigation started because asking whether the load instruction or the add instruction was executed, or if register 5, had the value 800 in it. The real concern is about files and user events. Did the user download this file, or is there contraband, pornography on his computer, or various higher level events beyond CPU instructions, registers, hard disk sectors. So this is kind of the primitive history is what actually occurs, but it alone is not going to answer our questions. If this investigation is trying to answer certain questions, this isn't going to help us directly answer those questions yet. So we have to account for, excuse me, the abstract systems. So to define the abstract system, we actually have to define new finite state machines for various levels of abstraction. Again, the details we're going to kind of skim over for this discussion.